Good morning, students. See, we are looking at Unit 2. In Unit 2, I said there are 7 different topics. Okay, in these 7 different topics, we have completed slabs, cylinders, sphere, this overall heat transfer coefficient, electrical energy, critical radius of insulation. All these are completed. And variable thermal conductivity. In this variable thermal conductivity, there are 3 things like you have slab and cylinder, slab, cylinder, and sphere. These are the problems are there. Okay, I have completed the slab and cylinder. Sphere is left out to you, and I have added the question in that Google Doc. Okay, I request all of you to find time and in your free time, please try to go through this cylinder one problem I gave and the sphere. I have left it to you. So do it for yourself. The procedure remains the same. Only thing is, in place of cylinders 1 by r, you will have r square here. Okay, in place of cylinders r, you have to put 1 by r square and solve it. That is the only difference. So with that, I complete variable thermal conductivity, and I'll be moving to the fifth topic, that is the systems with heat sources or internal heat generation. Okay, so we are done with the first 4 things, and now we are moving to this one. So today we are starting the fifth systems with internal heat generation. Okay, so so this is your generalized heat conduction equation that I have put here. So what I will do is I'll consider a one-dimensional system and a steady state system with fusion. Okay, that is, till now what we have done is we have considered that the fusion is 0. Okay, now I'm not considering that fusion is 0, that fusion is there. Okay, I'll consider a slab like this. Okay, on the slab there is a temperature here T1 and here T2, and inside there is some internal heat generation. This can be due to the chemical reaction, this can be due to the nuclear reaction, this can be due to something that is coming into the play, not because of the temperature difference. Okay, if it is not coming in, if it is coming into the play not because of temperature difference, then it is called as a internal heat generation. Other than temperature difference, if the heat is being generated, that is internal heat generation. So that heat is there inside this, and that has been considered now. If you have to consider that here, this is one dimensional, so I can neglect the y and z. I can neglect the RHS also, but I cannot neglect this part, that is Qgen by K. So this will be there in my governing equation now. So the governing equation will turn out to be, the governing equation is dou square T by dou x square plus Qgen by K is equal to 0. So this will be our governing equation. Okay. Now, once I take the governing equation, what's my next step? I have to differentiate it, the integrate it appropriately so that I get the um, general solution. So first, I'm integrating it. When I integrate it, what I have is, okay, for clarity, what I'll do is I'll take the Qgen by K on the other side of the equality. So then I'll integrate. When I integrate, what happens is dou t by dou x will get. The integration of dou square t by dou x square is dou t by dx. If I do it on the other side, what I have is integral dx. So what I'll get is Qgen by k into x I'll get. Why I'm getting this x? Because integral dx will come here. Okay? So plus C1 I'll write. This is the indefinite integration, so I have to put the constant. Yeah. Now I'll do the variable separable. I'll take this dx onto the other side. So what it will be, dou t is equal to qgen by k into x into dx. Since this is only one variable there here, you can put a dx directly instead of dou t plus c1 into dx. Okay. All right. Now I'll integrate it. When I integrate it, integral dt is equal to this qgen by k is constant minus qgen by k. I can keep it aside into integral x dx plus c1 into integral dx. Because c1 is also constant, I can take it out of the integration. So next, when I do the integration, on the left hand side, I'll get simply t, integral dt is t, and then minus qgen by k into integral x dx. Integral x to the power 1 dx, that is x square by 2. X to the power of n plus 1 by n plus 1. So x square by 2 I'll get here, plus integral dx is x. So c1 into x I'll get, plus the constant I have to add here because I'm not doing the integration with limits. Okay. So next part is calling this as your generalized, calling this as my general solution. This is your general solution. You got your general solution. Now that you got your general solution, what is the next step to do? You have to consider the appropriate boundary conditions here. Okay. So how to consider the boundary conditions here? Let me write that. Boundary conditions. Okay. So see, when you look at this equation, what you can understand is it is in the form of a parabola. Okay, it is x square is there here and x is there here and the other y is t here actually. So y is equal to ax square plus bx plus some constant is the expression here. So what I can say is the temperature variation from this you can understand that this is temperature variation is parabolic. Parabolic. Okay, so the temperature variation is parabolic here. If the temperature variation is parabolic, it is always suggestible to take something called as a symmetry boundary condition. Symmetry boundary condition means it's a kind of a Dirichlet boundary condition itself. That is a temperature is known, but you'll consider the symmetry so that you can solve it easily. See, this is what you have here. This is your slab. This is T1 and this is T2. And for the sake of this parabolic thing, what I'll do is I'll consider something called as a symmetry on the other side, and I'll call this as T2. So that this is your x is equal to 0 and this is x is equal to L. On this side, you will have x is equal to minus L. Because the same thing you will have on the other side as a symmetry. So here you will get T2 and this side you will get x is equal to minus 1. Such that you are considering something called as a symmetric boundary condition. Okay. Now, from this, what you can write is yet x is equal to 0. What you get is temperature is equal to T1. Yet x is equal to plus or minus L. The temperature is equal to T2. Okay. So let me call this as 2. Let me call this as 3. And this equation, let me call it as 1. Okay. Now what I'll do, I'll substitute my boundary conditions into my general solution. So when I substitute my boundary conditions into general solution, what happens? Let us see. Let me substitute 2 in 1. When I substitute 2 in 1, what happens is t is equal to x square of 0 is 0 again, plus c1 into x is 0 plus c2. So from this, what you get is the c2 value will be equal to the t1. C2 value is equal to the t1. That's what you get. And then I'll substitute 3 in 1. That is my other boundary condition. Okay. When I do that, what I'll do is first I will substitute the plus L value. Okay. I'll substitute the plus L value. Plus L will imply that the T2 is equal to minus Q gen by K into L square by 2 minus, I will take plus because I'm considering plus L into C1 into L I'll get in place of X plus C2. This is what I'll get. Let me call this equation. This is 3, right? No, I'll call this as 4. This is 5. And then now I'll substitute minus L now. When I substitute minus L, what will be my T2? I'll write it now. Q gen by K into L square by 2. This remains same, only this thing will become minus. The other things will be as it is. So this I'll call it as equation 6. So now what I will do is I'll consider these two effects. Okay, when I consider the effect of these two, I'll get something called as C1. Okay. If I don't take this plus or minus L, it will be impossible for me to calculate what is C1. So since this is symmetric boundary condition, I'll be in a position to calculate what is the C1. This should be written as C1 actually. Sorry, this is C1. So when I do 5 minus 6, that will imply everything will get cancelled. Only 2 C1 into L equal to 0 I'll get. So that implies L cannot be 0, 2 cannot be 0. So C1 has to be 0. So the C1 is 0 and the C2 is T1. Okay. So that's how you got your the arbitrary constant values. Call this as 7. Okay. So what you do now is you substitute the values of C1 and C2 into your expression 1. That is 4 and 7 in 1 will give you T is equal to minus Q gen by K into X square by 2 plus 0 plus, in place of C2 I can write T1. So from this what I get is T minus T1 is equal to minus Q gen by K into X square by 2. Let me call this as 8. This I got. And what I want is, I also want something called as T2 minus T1. Okay. I want T2 minus T1. For that, I can take either 5 or 6 because you have T1, you have T2 here, and this T2 is nothing but T1. So from 5, what I can write is, from 5, what I get is T2 minus T1 is equal to minus Q gen by K into L square by 2 L get. The C1 effect is getting 0. Let me call this as 9. Now what I'll do is, I'll do 8 by 9. That is, I'll divide both things. So what I get is T minus T1 by T2 minus T1 is equal to the whole thing will get cancelled in the numerator and the denominator. What I left with is x square by L square. So this is how your equation will turn out to be. Okay. See, if you remember, this equation is x by L for a simple slab. Okay. Now that you got a internal heat generation here and a parabolic variation of the temperature, you got x square by L square. Okay. For slab with Qgen is equal to 0, it is x by L. Okay. Meaning straight line variation. Here, slab with Qgen not equal to 0, it is x square by L square, meaning parabolic variation. Okay. I hope it's clear. If you have any doubts, you can ask in this one. Yes. Questions, please. You don't have any questions? Okay. Let me move on to the problem based on this one. I have updated this problem in your Google Doc. Please refer to the Google Doc. Right. So this is a question given to you. A slab of thickness 12 centimeters is given, and it is generating 10 to the power of 6. So this is your Qgen. Qgen is given in this question. So it is 10 to the power of 6 watt per meter cube. It should not be neglected in this case. K is also given. It is 200 watt per meter Kelvin. And both surfaces of the slab are maintained at 150 degrees centigrade. See, this is the key thing here. Okay. What he's saying is, he is saying that both the surfaces of the slab are maintained at 150 degrees centigrade. Okay. This both surfaces is very much important to consider here. See, he is not considering just the symmetric boundary condition. He is saying that whatever the wall that is there here, on this side it is 150 degrees centigrade. On this side also it is 150 degrees centigrade. Okay, what is the meaning of this? The meaning of this is the temperature is varying like this. The temperature is varying because you have given Qgen in your question, so this must come into your mind, and this is how you should consider it. Okay, so you should not say that the temperature is not varying at all. It's varying, but since there is a Qgen in the question given, so it's going to increase for some time and then decrease for some time. So here, if it is given 12 centimeters in the question, okay, so how do you solve it here? Okay, if you have to solve it here, whether you will take 12 centimeters thickness here or you will take 6 centimeters thickness here. Somebody please respond.
Sir, maybe 6.
See, this whole thing is 12 centimeters as given in question. Okay. What if you take it is 6 centimeters, the half of it. Okay. Whatever the formula that you have got here, you have got it for the half only. You did not derive it for the whole thing. I have derived it for this L. Okay, the positive L, that is, this is equal to 0, this is equal to plus L, this is equal to minus L. So what you have to do is, whatever the L you consider here, it should be the half of the thickness that is given. So these are the things to be considered. Okay. Once you are clear with these things, whatever he is asking you to find in the question, you can find out. What he is asking is temperature at the quarter planes he is asking. Temperature at the quarter planes he is asking. Means here you have to find out. Here and here. That is x is equal to minus L by 2. You have to find out. X is equal to L by 2. You have to find out. And x is equal to 0 also you have to find. I think these three things you have to find out. So what is the formula for temperature here? Somebody please tell me what is the formula for temperature here? Yes. What is the temperature formula here? See, the temperature formula is actually this. This is your temperature formula. Okay. How can I say that this is my temperature formula? Because uh, instead of this, I can write it this one. Okay. Anyone you can take, and from this you will get the temperature. So temperature is equal to, what I can write it is like T is equal to P on wall plus Qgen by K into L square by 2. That's how we get the expression. Okay. This will be even more clear to you when I do it in the next class. Okay. So for now we take it for granted. So P is equal to, I should get at x is equal to, or L is equal to L by 2. I want to get. Okay. L by 2 means what it is? 3 centimeters. I have to substitute now. So the T wall is given as 150 degrees centigrade, plus the Qgen is given as 10 to the power of 6, and the K value is given as 200. The L value is 3 centimeters, so 3 into 10 to the power of minus 2 meters whole square by 2. So somebody tell me what is this value. Calculate and tell me what is the T at 3 centimeters. What is the value? Yes, somebody please respond and tell me what is the value of this one.
240.
What?
240, sir.
240, yeah. 240.
Yes, sir. No, 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 sir. Yes, sir.
152.2.
152.2 degrees centigrade. Thank you. So, so one thing, okay. So if I have to find Tx, the formula will be T naught minus Qgen by K into x square by 2. Okay. So this is for finding. Yes. Harish, please switch off your. Yeah. So Yeah, this is a you get the expression, and then here you substitute. Sorry, there must be a mistake. This should be taken for the 6 centimeter system. See, I've changed this to 6 centimeters. Please tell me what is the value now.
159.
159. That's it. 0 degrees centigrade. Okay. Now this T naught is nothing but your T max. Okay. This is the your T naught. This is equal to 159 here minus q gen by k is 10 to the power of 6 by 200 into now the x is 3 centimeters now. I will put this as 3 centimeters. So this will be 3 into 10 to the power of minus 2 whole square by 2. Now tell me what is this value?
161.25.
1? See, it will be
161.
less. It will be less than 159. You should have minus here.
Sorry, sir. Sorry, sir.
156.75.
156.75 degrees centigrade. So you can put it at plus 3, you can have it at minus 3. So all the quarter plane temperatures are known to you now. So here the temperature is 159 degrees, and somewhere over here, if I take a pill here, this one also is here. So the temperature is 156.7. Here also 156.79 degrees centigrade. See, this time the plus are this minus. So how did I get all of that? Okay, that's the important thing to be considered here. See, if I want in terms of T1, this is actually T2. Put the other color here. This is T2, and this is T1. So the T1 will be T max. Right? So what I'll have here is T1 here, and this one will be T. So that's how I got these expressions. Actually speaking, these things, what we will do is, we will actually take them from the data book and solve it. Okay. Since this is the first case I am considering in your internal heat generation case, I have gone for the derivation. Okay. From the next case onwards, I am not going to do it this way. Okay. I'll be going directly to your data book. From your data book, I'll get these formula. Okay. Whatever the formula that are there here, okay, this formula will be directly taken from your data book. Okay, from next class onwards, that's how we will do for the different cases like your sphere, for cylinder, for various cases that are present in the internal heat generation case will be taken from the data book. So what I request all of you is have your data book with you for the next class. If you don't have data book with you for the next class, you will not be in position to understand what we are doing. So our data book is must for the next class. Okay, so keep that in mind, and then we'll solve almost all cases of internal heat generation, QGen, in next class. Okay, because tomorrow um, we'll be having 3 periods. Why? Because the lab session also I'm going to take this, and hopefully I'm expecting that this fifth topic, that is internal heat generation, will get completed in the next class. Okay, so keep that in mind. That's all for today from my side. If you have any questions, you can ask, or I take the attendance.
Sir, why did you take L by 2 value as 6, sir?
Yes, ma. Where, ma?
In the T max.
Here. Here, why L by T is my 6? Is it your question?
Yes, sir.
Where? Here. Here. Is that your question?
No, sir. Can you
Where,
scroll
ma?
down?
Hmm.
Sir,
No. This should not be L by 2, ma. I'm sorry. This is T max I'm considering here. This is L itself. Okay.
okay, sir.
That's a representation problem. Otherwise, it's fine.